Hello and welcome to my talk. I'm Arnd Bergman. I'm talking about code refactoring today, and I want to thank you all very much for staying for this kind of talk just before the lunch break. If you make it to the end without falling asleep, I have chocolate. I'm going to do a brief introduction for anybody who doesn't already know how system calls work in general. So can you just please raise your hand if you have looked at how a system call works? Have you read the code, please? That's about 2/3. Good. I'll do that introduction then. I'll talk about how the current tables are generated. So there's two major things. There's the actual tables, which are quite complicated, and I have some plans for refactoring those. And then the macros that we use. So we have a lot of nested macros for each system call that get expanded in a weird way, and I have plans to replace those. And then I have some other ideas what we could do to improve all this, because right now it is fairly complicated. So the simple version is, for those who don't already know, system call is just a function that you call from userspace that is implemented by the kernel. So a read function is implemented roughly by calling the libc syscall function, which is then calling an architecture-specific instruction. And that ends up in the kernel in code that I'm not showing. When it gets to C code, we get to something roughly like this, where we have the user space registers. We have an array with every single function. There's about 400 of them. And we just do an indirect function call, pass the registers. And so there's the table. These are some of the system calls we have on ARM64. So you see that the read system call is number 63. And then we have a macro that gets expanded to a function like this. We read every argument from the user space register structure. And that calls several internal functions, ends up in something that's called sysread, and that then usually calls another function that in this case is called ksysread, and that is the actual implementation. And then we are in C code that somebody has written. And it's a little more complicated in practice, and I'll get to those complexities in a bit. So why do I want to clean this up? So we have 21 architectures, and they all do this slightly differently. So there's a lot of commonalities. Pretty much every architecture has copied from one or more of the existing architectures when they introduced this, but they all have some quirks. And some of the quirks are fundamental to the architecture. Some are needless, and we can remove them. But most of it is completely unreadable, and that is particularly bad because if you make a mistake there, you have an exploit waiting to happen. So I want to make sure this gets as readable as possible and as common as possible so that we have the same bugs on all the architectures. And the exploits will be portable, yes. And it sounds like fun, right? So let's look at the table generation first. We have two kinds of tables. So in a work that I did together with Firoz Khan here in Linaro, like 7 years ago, we converted most of the architectures, so 13 of the still remaining ones are converted to a table format that looks like this. So you have the system call number, you have an ABI qualifier that says what type of ABI this is, and these are all common ones. We have a number, we have the name of the macro, like the __ number read that we saw earlier, that is this name, and then we have the name of the system call function in the kernel. Most of them match, but not all of them. And then we have 8 architectures that were added late enough that they have the same numbers. So that's another work that I did a while ago, that all new architectures can share one table instead of having each architecture make their own decisions about which system calls to implement and what numbers to give them inconsistently. So these are all consistent, but they don't use the modern format. So they use a completely different format to have the same information as the older architectures, and that is just crazy. So the first thing I did was to actually convert this table format into this format, but keep all the information intact, and that turned into something like this. So this is the format we have. So we still have number, ABI, macro name, entry point name, and then compat entry point name for those architectures that support both 64 and 32-bit user space in the same kernel. There are a couple of system calls in the middle that are architecture specific. So OpenRISC, for example, has one system call that's not in the others. RISC-V currently has 3, I think, and Arc has 5. But these are all, I just gave them a different ABI name. So we have names for the 32-bit time system calls that are used by everything except RISC-V 32. We have the ones that are only used on 64-bit architectures. So you see number 4 is either the IO get time events time 32, or it's the IO get time events, depending on whether you're on a 32-bit or 64-bit architecture. And there are more corner cases like this. And then that required a makefile. So every one of those 13 architectures that have the modern format has a copy of this makefile. And they all have some minor quirks in there, so they are not all identical. And then here there's a list of the ABIs that an architecture needs. A new architecture would only need common and then either 32 or 64. And these are all the other ABIs that might be optional. And this makefile, so who understands this makefile syntax? Please raise your hand. So that's very few people. Oh, that's more than expected. So at least 10 people here. But it's pretty much unreadable. And that's only part of the makefile. There's more here. Even if you understand most of the kernel makefiles, this is particularly bad. So I have made a common makefile that gets included automatically. And then you just have one new makefile that contains a couple of lines that are easily understandable, even if you do not know how the k-build system works. So you just define variables. You say the name of the table file per architecture, and for each ABI, for each output file, which of the ABIs are enabled. So PowerPC and MIPS each have 3 ABIs that they support. ARM64 has 2 ABIs. On MIPS, we have 3 input files. On PowerPC, we have 1 input file. So they're all slightly different. But I've converted all 21 architectures to use a file like this, and that seems to work great. I still need to verify that the data is actually the same as before, but it's looking good. Probably a couple of mistakes in there. And this is what I actually had to put into a generic makefile that already exists in the kernel. So instead of having all of this that's duplicated from common code, I went to one makefile that already exists and have a slightly more complicated rule that then works for all the architectures. And you don't even have to understand it, you just have to use this if you're an architecture maintainer. Then there are kind of bits that I'm still working on. So these are not working yet. I want to have one table for all the system calls above 403. So right now, current state is you have those 25 files for the 21 architectures. Every time somebody adds a system call, you have to edit all 25 files. And after I convert the table format, you add the exact same line to each one of them. So this line would be the same in all 25 files. And then the obvious question is, can we make it work to have just one file. So if you add a system call, you just added one file, and then it automatically gets included in all the architectures. And it's not that hard. The only complication is alpha, which has different numbers because they have more system calls, and we ended up like they have 110 system calls more than all the other architectures. So there needs to be a small quirk in that. But other than that, I think that's what we'll end up with. So we have one file that starts at number 403, and that then gets used by all the architectures. There's minor complications, like clone 3 is currently implemented on all but 3 architectures. I'll probably have to enforce that it's the system call exists, but then on those 3 architectures it just returns an error until those get fixed. And we just fixed alpha. Then the other quirk that I want to work on is the stupid naming. So in the time32, time64 rework that we did a few years ago, the state that we left with was that we renamed the entry points for those system calls that take a 32-bit time t to have a time32 suffix, but we left the macro unchanged. And for the new system calls that were added, we changed the macro, but we used the old entry point. And the way that I want to rename this all is to have consistent naming. So there's then a futex time32 macro and a futex time64 macro. And all architectures would implement those. And then we rename the functions accordingly. And that just makes so much more sense. So we don't have to worry about, like, if you're reading this, you don't have to constantly question, like, which one am I? And then we just need something that defines the old macros conditionally based on where you include it. And I hope maybe we can even remove the old names from the default header, because we have a ton of bugs. Like Debian is currently doing the transition to 64-bit time t. And I looked at a lot of packages that call futex, and almost all of them get it wrong because they end up still calling the number futex syscall, but with a 64-bit time argument if they pass a timeout. And that's obviously wrong. It works most of the time if you're on little endian, because the first bits are the same, but then any timeout under a second is completely wrong. Okay, then the other part is the wrappers. This is the bit that I've shown earlier briefly that get expanded. So this is the top level of macros, and I'm sorry if you've ever had to look into how this works, because most of the time it doesn't. If you look into it, it's because it doesn't work, and it's very hard to understand. If you ever want to insert a backdoor, this would be the place to do it. And this is how they get used. So back to the futex example, there's you have this macro that gets expanded, and then you have the normal function definition here. And this actually turns into, depending on the architecture, up to 8 functions, I think. And this is what the macro looks like if you expand it. Obviously, no one is going to be able to read this. And the reasons why we have all this complexity are quite obscure. It's mostly got to do with sanitizing the argument. So one thing that happens is if you pass a 16-bit system call argument, the ELF ABI on the architecture may require that the upper bits are 0 extended or sign extended, but then nothing enforces this on the user space side. So user space can just pass a value, if it's malicious, that is not following the ELF ABI, and that can cause random behavior in the kernel. So we actually have to make sure that these macros sanitize the arguments in a way that whatever we pass to the actual function is at least compatible with the ELF ABI. Otherwise, the compiler may get confused to the point where we just jump into the wild to some random address, in the worst case. Same thing can happen for compat functions where you have a long argument that is 32-bit and 32-bit user space, but then you have something in the upper 32 bits. What I want to do is have code generated that looks like this, that is actually readable. Might have to be a little more complicated than this, but pretty much you should be able to see exactly what's going on and have all of these wrappers expanded in one file that is generated from one machine-readable table that describes every single system call. So I want to make sure that the name of the function, in this case, futex, would uniquely identify the signature of the system call across all architectures. And then this part would be architecture specific again, but then call into a generic function. And you would be able to see what is going on from looking at it. The good thing about this is once we have this information and know exactly in a machine-readable format for each of the hundreds of system calls what are the arguments on a given architecture and which system calls exist, we can share that information with a lot of projects that need the same information. So glibc has tables that duplicate the same information. They probably want to keep these tables, but at least we can have a table generated that makes it easy to compare the two and see that we're actually talking about the same calling conventions. The user space wrappers, so one part, I mentioned futex already. One part that it does is there's no way to call futex portably from user space because glibc doesn't implement a wrapper for historic reasons. Could just never agree on what the function signature should be. So everybody who uses futexes needs to call syscall directly, and they all get it wrong. I want to have automatically generated headers in the kernel that for each system call that the kernel supports has a function you can call after including this header. The QEMU has code for emulating user space for one architecture on any other architecture, and there's some handwritten code at the moment that converts the calling conventions if they don't match. And a lot of that can probably be generated once we have this information, but I have not actually looked into what's necessary for that. And then strace and perf are the projects that have a list of all the system calls. They need to know the name of the system call, the number, and the arguments, and that's, I'm sure there's more of those. Another example would be language bindings for Rust and Python. Anything that is not C but wants to call a system call might need to have the same kind of wrappers, and we can generate them all once we have this information in tables. And then the 128-bit architecture is something that keeps coming up. We had Morello, and there are other bits. There's RISC 538, and we'll eventually have to get there. This is one of the steps we need, so that when we have the function signatures, we can create those macros for 32, 64, and 128, which at the moment we cannot. So that's going to make this a little bit easier. And that's all I had. So questions? Yes.
After all the table generation and other bits and pieces, what will be the effective license of the user space headers?
I don't know.
Because it's interesting whether they can be used in just GPL license code or whether they can be used in other bits of code.
Right. So since I would be the one writing those generations, we can probably choose a license that would be appropriate. There's, yeah, I don't.
It can be awkward, but it's definitely worth thinking about when you. If that's part of your ambition, I think it's worth thinking about.
Yep. So I don't know how that works when you have generated code and the input to the generator is under an existing license.
Yeah.
But yeah, we can certainly think about that. Make it as open as possible for this.
Oh, it's another one, don't
you mentioned for the syscall marshalling with those horrible macros and whatever.
Yep.
So So I wrote the ARM64 version largely copying from the x86 64 version. I know that some of that, like the SE sys stuff, is not really necessary because that's the sign extension thing, and our procedure call standard rules mean that we just ignore the upper bit. The callee ignores the upper bit to the registers anyway.
Yep.
So I know that we can get rid of that. And on the next slide, I think it was when you said you wanted to do, or not that slide, the one where you had that one.
Yep.
You said that latter part was going to be still generated architecture specific, or are you going to do that generically?
I'm not sure. So I expect that it will have to be architecture specific, but we'll have to see.
Okay. I was just going to say that because I know that the reason that I copied that stuff, even though it wasn't strictly necessary, was just to align so when any future changes came in, we could do the same thing. I suspect we probably want to make that common, even if it's a little bit more verbose.
Yeah, so I've already reworked it a couple of times. So I think the original version came from S390 that was copied into x86, modified there, and then modified into ARM. And then I modified it again for S390 because the other ones had added features that were not in S390, and I noticed that S390 was broken, and there was still something where ARM, I think, is broken. And like, once we have this version, we can actually see if it's broken or not.
Fair. Just one last thing. For the generation of that, are you expecting to generate that at build time like we do for syscall tables today, or are you expecting to do that every so often like we do for the atomic headers?
I haven't decided.
Okay.
Yeah. So either way is possible. Generating it in advance would have the advantage that for the tools directory, we could have the generated copy rather than having to generate another copy and copying the input files and maintaining those.
Yeah, I just remember that one of the reasons we generated the atomic files and committed them was that Linus wanted to be able to look at them to read through them. And if we were doing this to make it readable, it seems to align better.
Yeah, that's a good point.
Yeah, so do you have some performance tests? Yeah, it's exhibited some more instructions in the syscall path.
I have not done any performance tests. So far, I have not done any changes that would change the actual output from the compiler.
Okay.
So I would definitely hope that it will be a bit identical. With these functions, it depends on how we do it. It's possible that we add a few cycles to every single system call, and if that is a problem, we might have to do something slightly uglier than I would hope for.
Okay.
If we can spare an extra branch, for example, it would get a lot cleaner.
Yeah, I think one of the reasons the current stuff is so ugly is that it's all set up to be always in line so that redundant stuff can get optimized away entirely. Like for example, some of the casts here just will expand to absolutely nothing.
Yep, and I want to get even further. So I wonder, one of the things I've been thinking about is having a check for whether this is actually called, since we know which of these are referenced by the tables, and then if we just return, like if we completely remove this, then we can inline it better if there's two callers, but only one of them is actually used. So that might actually improve things.
I look forward to seeing patches on the list.
Okay. Yeah, I'm up to 30 patches now, and I only have half of this implemented. So it will be a little longer. But I can probably start sending the bug fixes for bugs I found in the process. Okay. And I think that's it. And there's chocolate.